Miri is Rust's interpreter, and Christian will gladly debate her on how to bequeath her the stuff underneath, so she can run until much later.
Okay, thank you. So this talk is called Miri, Undefined Behavior and Following Functions. So, but before even we begin, let me just introduce me a bit myself. So I'm Christian Poveda, I'm Colombian. As you already know, I'm a PhD student at the India Software Institute. Occasionally, I contribute to the Rust compiler project and also to the Miri project. I don't work on it like full time. I just do it like when I have free time. So first of all, I want to say what I want to give this talk, what I think this is important somehow. The first thing is that unsafe is a controversial topic in our community, but at the same time is something that we need, is something super special that Rust needs to work and to be able to do the awesome stuff that it already does. So basically every program you have uses unsafe in one way or another, even if you don't know it. And it's super important to have awareness of the implications of what happens when you use unsafe incorrectly, or if someone else does. And also, I want to show you a super cool tool that you can use to write better unsafe code that helps you when your unsafe code is wrong. Because this goes in the same direction as the empowering philosophy that the Rust community has of being able to build reliable software, and at the same time having a super friendly community with a bunch of tools that help you to build that. So it goes in that direction. This talk will have like 4 parts, basically. First, I'm going to show you a bit, do a little introduction to unsafe and what's undefined behavior and how that everything works in Rust. Then we're going to talk about Miri. Miri is this super cool tool I'm talking about. And then we're going to talk a bit about foreign functions. And if you like this, you think this is interesting for you, I can give you some ideas at the end on how can you help contributing in all of this. So let's begin by talking about unsafe Rust and undefined behavior. Before even talking about undefined behavior, I think it's super important to know or to discuss why people use unsafe Rust in the first place. There are 2 main reasons. The first one is that some people use unsafe because they are very invested in performance. They want their programs to run super fast. So they are ensuring everyone that their programs are running correctly, even if those programs doesn't have any check to be sure that they're running correctly, and not doing a lot of checks. Let's just squeeze a little bit more of performance when you're writing your programs. And there is a lot of controversy around this one. Some people say that, yeah, performance matters, but safety is first. There are a lot of trade-offs you can do there. But the second reason is a little bit less controversial in the sense that many projects we have in Rust need to interact with other languages or with your operating system or with a bunch of resources that aren't written it themselves in Rust. So most likely you will have to interact with a C or C++ library or use a crate that interacts with a C or C++ library. And those languages doesn't have like the same guarantees that Rust has about safety and having sound programs and so on. So all those functions that interact with C libraries are unsafe too. So now we can discuss what unsafe can do. So inside unsafe functions or unsafe blocks, any of the 2, there is not much you can do actually. You can do only 5 things, not anymore. You can dereference raw pointers. You can call functions that are marked as unsafe. So if you have a function that is called unsafe fn and the name of the function, you need to use unsafe to call it. You have to do it in an unsafe block or in another unsafe function. There are some traits that are marked as unsafe too. So if you want to implement those traits, like send and sync from the standard library, you have to use unsafe. If you want to mutate the statics because you are sure that your program needs some sort of mutable global state, even if some people don't like it, you can use unsafe to do that. You can use unsafe to access fields of unions. Unions are like enumerations, but they don't have like this consistent tag to distinguish each variant. So it's like you can literally join two types at in a single one and use every value of that type as any of the possible variants at the same time. So you need unsafe to access those fields. However, for the purposes of this, we're just going to focus on the first two because those are like the more common. Most likely, any of us has been exposed to one of these at one point. And given that the first one is the referencing raw pointers, I think it's worth to discuss raw pointers for a moment. So, what are raw pointers? Many of you, if you have already used Rust, you know that we have references, we have ampersand mute and ampersand for mutable and immutable references. But those types has like these two brothers or sisters, siblings, whatever. They are called raw pointers. We have star const and star mut. Star const is an immutable raw pointer, and star mut is a mutable raw pointer. And they exist because they don't follow the same rules as references. They don't have these liveness constraints. For example, if you have some data and you create a pointer to it and you drop the data, it goes out of scope, is deleted, you can still have the raw pointer to it, even though it's pointing to something that doesn't even exist anymore. So for these reasons, there is something else, and you can also like offset those pointers using integers. So if you have a pointer to a particular memory address, you can add it like an integer, a new size to it, and you can offset it so you can read like another part of the memory, and maybe you're not supposed to. For those two reasons, those pointers might have a lot of problems and might misbehave in several reasons. You can have null pointers that are raw pointers that doesn't point to anything really. They can be dangling. There are pointers that, let's say, are pointing to something that doesn't belong to us. So if you are inside a vector and use a raw pointer from inside the vector to access something outside the vector, that's a dangling pointer. Also, if you have a pointer that you offsetted a bit, but you didn't do it correctly. So for example, you have a pointer between, I don't know, U64s and you just moved, I don't know, 16 bits instead of 64 bits, you will end up reading like in between values. That's an unaligned pointer. And okay, so those are raw pointers. You can do like a lot of nasty stuff with them. We are not sure why that's wrong really right now. We will go into that later. But let me show you an example, a super tiny example of how to use these raw pointers and how to use unsafe and so on. So here in my terminal, in my editor, I have this tiny crate. It has a single struct. It's called byte array. This byte array has a mutable raw pointer to an U8 and has an U size that represents its length. You can think of this type like an slice, or if you want, like a vector. But here we only have like two simple functions. We can only read stuff from it. We cannot grow it or make it smaller. We can just read stuff from it. And usually what happens in the Rust ecosystem is that you have like these two functions. You have like the unsafe, unchecked version of a function, and then you have the safe version of it. Here we have the unsafe function. It's called getUnchecked. It receives an index, and what this function is doing is that it takes this pointer, PTR, casts it into a new size, then it adds the index to it, and casts that integer back to a pointer. So we are offsetting the pointer by adding index to it, and then we dereference it. Actually, all of this code, all these three lines are not required to be done inside an unsafe function. The only thing that is unsafe is reading from the pointer, calling the reference star operator over it. So you can use raw pointers however you want, but if you are going to dereference them, you have to use unsafe. And then we have like the safe counterpart of this function. So we guarantee that if the index you're reading is out of bounds from the length of this array, then we return none. And if we are sure that we are in bounds, then we just return some and do an unsafe call to this get unchecked function. And when you run this, for example, let's say this is a crate in the Rust ecosystem, is in crates.io, and someone else decides to use it, they might just do something like this. They just import our library, use this byte array type, call a function that I didn't show because it's not relevant for the purposes of this talk, that is called zeros, that just create an array full of zeros. And they might need to use unsafe because they need to go super fast with this thing. So they are just going to use get unchecked and 0. And if we run this, it returns 0. So it works as intended. Some of you might be asking what happens if you do this. You call this function with a larger index. We'll get to that later. So yeah, that's the demo. And the big question now is, well, actually, what can go wrong when you use unsafe? And you might have heard answers like, oh, if you use unsafe wrong, then you're causing undefined behavior, or undefined behavior is super bad. Anything can happen when you're dealing with undefined behavior. So let's discuss a bit undefined behavior. Let's say the Rust compiler was written under certain assumptions about how programs work. About the programs we write programs that need to meet certain conditions so the compiler can actually compile them into what we want. If we break any of these rules, we say we're calling undefined behavior. As Stefan said, this is a way of saying, like, if there is something that is not actually specified by the compiler in a clear way, if the compiler is trusting that to happen, and if you break that rule, then you're causing undefined behavior. There is something super important, is that undefined behavior is different in each language. So C has a lot of rules for undefined behavior, and those rules are not the same for Rust. For example, what Stefan told you about adding an integer and going, let's say, going out of bounds in the integer, like adding too much to an integer because it can fit a number too big, then that's not undefined behavior in Rust, but that's undefined behavior in C. Because both compilers were built with different guarantees in mind. And actually, the list of things that Rust considers important rules when we're dealing with undefined behavior is a little bit tricky. So I'm just going to mention some of them. Your program might have undefined behavior if you are dereferencing a pointer that is dangling or unaligned. Also, if you try to produce, or if you manage to produce a value that is incorrect for their type. So for example, Booleans, when you look at the actual memory, let's say, Booleans are represented by bytes. They take 1 byte exactly. So you have a 1 or a 0, but a byte has like 8 bits, so you have a lot of values that you could use. So 1 is true, 0 is false. But for example, if you take a 3 and you try to put that into a Boolean, doing that is undefined behavior because 3 is not specified as a Boolean. The compiler doesn't know what should do if it sees a 3 instead of a 1 or a 0. Causing data races is also undefined behavior. And as I said before, there are a lot of subtle rules that must be taken into account here. So what happens if we break these rules? Basically, Rust cannot work correctly. We lose this guarantee that Rust has that of producing programs that do what we want them to do. Rust can no longer compile a program correctly. So what this means is that in the best case, your program might not run. Maybe it throws a segmentation fault or some sort of memory out of bounds error or something like that. But in the worst case, it might run, but not as you intended to. So that program might do anything. For that reason, it's pretty common to see this kind of psychedelic image with unicorns and rainbows and a lot of colorful stuff when people discuss undefined behavior, because when we are dealing with undefined behavior, we lose track of what our programmer is doing in the most basic level. We don't even know anymore. So there are good news for us, Rust developers, people in the Rust community. If we are using safe Rust, if we promise to never, never, never use unsafe, we don't have to worry about undefined behavior, because undefined behavior shouldn't happen in safe Rust. Also, if you are using unsafe and you are super sure you're not causing undefined behavior, you might actually get any performance benefits, or you can interact with C libraries and so on correctly if you don't cause undefined behavior. That's also good. There are also not so good news, and is that unsafe is a super important part of our ecosystem. Even if we are not causing undefined behavior ourselves, someone else in one of our dependencies might be doing it. Here I have like some super interesting statistics about this. 20% of all the crates that are in crates.io use unsafe directly, and 74 sorry, and of those 20% crates, all those crates, 74% of them do unsafe calls to functions that aren't in the same crate. So are crates that are using unsafe to call function that are either in the standard library or in other crates. If you want to get like more information about these metrics, you can Google or use your favorite web search engine to look for this paper about how do programmers use unsafe Rust. But my point here is that unsafe is everywhere, not because people are not good doing their job, but because we need it. We actually need it. It's everywhere. And so I also have good news, actually the best news, and is that there is a tool that you can use to detect undefined behavior in your programs. And the spoiler is in the title of this talk. It's called Miri. So let's talk about Miri. If you want to take a look at the Miri repository now or maybe later, this is the URL. You can find all the code in github.com/rustlang/Miri. So what's Miri actually? Miri is a virtual machine for Rust programs. This means that Miri doesn't compile your program, it interprets it in the same sense that the JVM interprets Java code or byte code, or that the Python interpreter runs Python, or that the Ruby interpreter runs Ruby, and so on. Miri is like that, but for Rust. And it has a super cool feature that none of the other interpreters has, and is that it can detect almost all cases of undefined behavior while running our code. And okay, there is also something interesting, and is that some of the code that is used in Miri is used in the engine that does compile time function evaluation. So if you have any const item in your program, you have a constant, you have a const function, part of the Miri code is used to run that function or to evaluate that constant. So it's pretty common to hear stuff like, oh yeah, Miri is the constant evaluation for Rust. But here we will be talking just as Miri as just the standalone tool outside the compiler that can interpret your programs. So how to use Miri? You need the nightly version of the compiler to do this. So if you have rustup, you have to install the nightly toolchain. You can do this by running rustup toolchain install nightly. And then you can install Miri just as a component. So it's the same as installing Clippy or Rust FMT or whatever. You just have to do rustup component.miri. And then after Miri installs, it has to download some additional stuff. It takes a while compiling, but you can run binaries. You can run your whole program if you want with Miri, or you can run just your test suite if you have test. Okay, so let's do a tiny demo with the same code I was showing you before. So again, we have this super tiny super tiny program that is using an external crate, let's say, that is using unsafe. And maybe the person that is writing this program doesn't know about the guarantees that crate has to be sure that these functions don't cause undefined behavior. So you might be tempted to do something like, I don't know, why can I read the 11th position of an array with 10 elements? Like, who is stopping me? The compiler is not complaining. So if I do cargo run, it works. It actually returns 0. That is a perfectly good value because it returns the same as before, so it's fine. But if you run this with Miri, you will find this super cool error that says undefined behavior. Pointer to allocation was dereferenced after this allocation got freed. And it points to the part of the code in the original crate that causes this undefined behavior and is a pointer to reference. And you can see more information and so on. But the important part here is that what's happening in the model of execution of Miri is that this function is creating a pointer that is dangling. You created a pointer that is outside the actual range of the vector. So when the vector gets deleted, because Rust deleted it after everyone has used it, you still have this dangling pointer pointing to nothing. But for example, if we go back to the perfect case where we didn't have like any undefined behavior, we can just do cargo Miri run, and Miri won't complain and will return the same as your regular program. Okay, so that's like how we can use Miri. We can use it to detect undefined behavior if our program is causing undefined behavior in that scenario. But now I want to show you, I want to discuss a little bit like how Miri works actually. And to talk about how Miri works, we have to dig a little bit on how the Rust compiler works. So this is like a super high level overview of the Rust compilation pipeline. These are like more or less all the stages that a program follows when it's getting compiled. So we always start like at source code with our .rs file and end up in machine code, or in a binary, a wasm binary, or a dynamic library, something like that. And what happens in the middle are like basically 4 stages. The first one is parsing. So Rust reads the text of your source code, let's say, and parses it to produce an abstract syntax tree, or AST. Then this AST is transformed and processed to produce a high-level intermediate representation, or HIR. In this stage is where most of the type inference process happens. So a lot of types are inferred here in this stage. Then this HIR is lowered to another representation, intermediate representation, but this is a mid-level intermediate representation, MIR. And here is where the borrow checking happens, most of it. In the MIR also is when the compiler does some optimizations about your code. And after that, we start interacting with LLVM, that is a backend for compilers that Rust uses. And this LLVM project also has their own intermediate representation. So we lower MIR to the LLVM intermediate representation. And LLVM does a lot of optimizations over your code. And finally, LLVM does the code generation to produce your binary file or your library or so on. Miri works almost in this way. The only difference is that the code generation stages don't run, so we don't get to talk with LLVM. What happens is that Miri lets the compiler run until you have the MIR of your program, and Miri interprets that MIR as if it were bytecode. So if Java has bytecode in the JVM, Rust has MIR when running Miri. So that's why Miri is called Miri, because it's an MIR interpreter, Miri. I'm showing you this because here is something super important, is that Miri cannot interpret programs that aren't Rust programs. So you have a C library that you run with your Rust program. Miri cannot interpret that in any way. That program doesn't have like the same syntax. The compiler doesn't even understand that program. So you cannot interpret that using Miri. And there are many limitations, actually. There are some limitations that Miri has. Miri is not perfect. It's not a silver bullet for all your undefined behavior problems. Another limitation is that Miri is slow. So if your test or your program is performance sensitive, Miri can take a while to run your program, even if it can do it. This happens because Miri has to do a lot of runtime checks about your pointers and about how memory is managed to be able to tell you when undefined behavior is happening. Um, and the other important point is that Miri can only detect undefined behavior if it's happening. So as I showed you in the example, we have a program that might have undefined behavior if someone calls a function with a certain argument. But if that doesn't actually happen, Miri won't warn the user about this case. Also, Miri cannot detect data races yet. There is no way to reason about data races. And again, Miri can only interpret Rust programs. This one is super important. You might be wondering, why does this matters? And it's because, well, programs don't run in isolation. We tend to use files. We tend to access files, get resources over the network, interact with databases, create OS stress. So we need to access the concurrency primitives of our operating system or whatever. And the mechanism that Rust uses to interact with all those are foreign functions. And that's where this last part is about foreign functions. Some of us might be, let's say, might be think that we don't need foreign functions at all. Maybe we have never used external FN in our project, so we think, no, that's fine. I usually don't interact with foreign functions. But I'm almost sure that anyone or almost everyone has interacted with the standard library to do any operation, to read files or whatever. And that means that somehow you're using foreign functions. For example, this is the stack trace when you call file open, the standard library function for opening files. There are like 6 functions here. The first two are like Rust functions. They are in the standard library. They are platform independent, so this works in any platform, in Windows, Linux, Mac OS, whatever. Then we have like 4 functions that are specific for Unix-like platforms, so those only run on Linux and Mac OS and BSD and so on. And then we have this Open64 function at the end. The funny part about this Open64 function is that it's not even a Rust function. It's a C function, it's the Linux system call to open a file. So this is a foreign function written in C, and it's an unsafe function. And Miri cannot interpret it. So what happens if in any of this process we have undefined behavior? Can Miri run that? Because it cannot interpret the Open64 function. The good news is that, yes, Miri can actually run your program in a particularly interesting way. And yes, Miri cannot interpret your foreign function, but it can intercept this call. So when you're running your program, if you call Open64, Miri will say, okay, someone is calling Open64. That's a foreign function that I don't know. That's not a Rust function. And then the Miri contributors can write whatever code they want to emulate that function. We call the code that emulates a function, we call it a shim, S-H-I-M. And if a shim needs to interact with the operating system or with any of the resources that the standard library provides, we use the standard library for that. So it's funny because the standard library uses foreign functions, but Miri uses the standard library to emulate some of those foreign functions. Let me show you. So instead, we are still in our example with the byte array crate, but in this case, we have a user that is reading the size and index that it wants to use from a config file. And this config file is read using read to string. Read to string uses file open, so eventually it will use Open64. And we're doing the same. We're just printing something after using unsafe. If we try to run this with Miri, we will get an error, but it's not because we're causing undefined behavior. We have this unsupported operation open. It's not available when isolation is enabled. So this is the Open64 function I was talking about. Open is not available when isolation is enabled. Please pass the Miri disable isolation flag to disable isolation. So if we do that, and set the Miri flags environment variable to Miri disable isolation, we can actually run the program. And in this particular case, it seems that the config file is actually causing undefined behavior. It says memory access failed. Pointer must be in bounds at offset 11, but is outside of bounds for the allocation, which has size 10. So this seems to be the same problem as before, that someone is reading 11, the 11th position of something with only 10 elements. And if we check our config file, yeah, it is exactly that. It's reading the 10th position, or the 11th if you want to think in zero base indexes. And that's the whole problem. So yeah, we can use Miri to detect undefined behavior even in programs that use foreign functions. That's super cool. And actually, other than handling files, Miri can do a lot of stuff. You can manipulate directories, you can delete files, create symbolic links, you can spawn threads, you can use logs and atomics if you're doing concurrency, so Miri can emulate some concurrency stuff. You can use it to get the current time, so you can actually like run clocks inside your Miri program, your Rust program running Miri. You can handle environment variables. And each of those operations is possible because someone decided to route a shim for that specific foreign function. And this has a super cool side effect. Well, not so side effect. Some people were actually targeting to get this working. And is that the standard Rust library works in many platforms. You can run it, you can use file open in basically any tier 1, tier 0 platform. So this means that you can emulate foreign functions even if you are not in the platform the program is going to be compiled on. So for example, if you have a program that is supposed to run in Windows, but you don't have a Windows machine, you can use Miri to interpret that program as if it were a Windows program. Let me show you. So here we have another user of our library. This time is using environment variables to set the size and index that it wants to read. And Miri can emulate an environment inside it, so we can use the size environment variable to set the size of the array. We set the index to 1 because we want to run that, and we disable isolation. And I'm using a Linux machine, but I'm going to run it for a target that is Windows. I don't have Windows installed here. And it works. And if I want to run it in anything else, I can do it. I'm running it on my regular Linux target and it's working. So this is super cool because maybe you can use Miri in one situation when you're not sure if this code that you wrote specifically for Windows is working correctly. Maybe you can use Miri for that too. Even if you're not using unsafe, you just want to be sure that your program runs as intended. And yeah, basically that's like the hard content of my talk. And I want to spend like the last few minutes talking about contributing to Miri. So if anything of this caught your attention, I encourage you to contribute to Miri for many reasons. My personal reasons is that I always wanted to work like in compilers because I find them super interesting. I really like Rust and I didn't know where to start. So I found Miri. I say like, oh yeah, I could implement like maybe some foreign functions for opening files or whatever. It sounds not too hard. It took a while I understood some Miri specific stuff, but it actually helped me a lot to understand how the compiler works and get involved in a lot of stuff that I wouldn't be able to do otherwise. Even then, if you don't feel comfortable yet contributing because, I don't know, you can help this project by just using it. Maybe you want to use it because you actually write unsafe and you want to be sure you're not causing undefined behavior. Maybe some of your dependencies use unsafe and you want to be sure that them don't cause any undefined behavior. So yeah, there is that. You can save yourself for a lot of others, many headaches debugging weird undefined behavior bugs. And maybe you're expecting that Miri catches something and it doesn't, or maybe the other way around. You think this program is correct and Miri is complaining. Maybe you can open an issue for that. You can talk with someone from the Miri contributors to discuss it, or from the unsafe working group also. Uh, there is something super important, and this is not like an obligation you have with the community. If your program runs really slow in Miri, that's fine. I mean, you don't have to give anyone coverage for this. But if you are super interested in contributing to Miri, writing a shim is a super easy way to start. Or if you want, just request it because you need it and you don't have the time, that's fine too. If you want to write it yourself, it's super cool because what you have to learn is actually like you have to read your platform specification about how that foreign function works. And the stuff that you need to learn about Miri is really small. You don't need to know how Miri works completely to do that. I don't know how Miri works completely. I just know some little parts here and there, and I implemented a lot of shims because I like them. Even if you don't need that, if you don't need that shim, maybe someone else needs it, and you are not just testing undefined behavior for the standard library. You're testing undefined behavior. You're helping everyone write better unsafe code because a lot of people use a bunch of shims that the standard library doesn't use, for example. If you want some specifics for Windows, many of the shims haven't been implemented yet, and that's sort of fine because you can cross-interpret like you were in Linux, sorry. But yeah, for example, if I go back to the program that opens a file, and I try to run it with the Windows target, it will fail, but it will fail because this function create file W has not been implemented yet. So maybe one of you want to do it. That's super cool. There are a bunch of stuff that haven't been implemented yet. And that's all. So thank you for your time. I hope you find this interesting, and I think we can do some questions now if you want.
Yes, the questions. So, where there was the demo with accessing the 11th element in the array, the error message said about accessing allocation, it was free. This was out of bounds. So I guess this is the question, how far can it track stuff, right?
Yeah, so this is not clear for me actually. Sometimes this program fails because when Miri interprets it, it frees the memory for the array before you read the pointer. So it complains about memory being freed. Or sometimes the array is not deleted yet, so it hasn't been dropped. So it complains about it being out of bound access, even though the array is still there. So the good news is that any of those are undefined behavior, so we're fine. But yeah, Miri tries to be deterministic as much as it can. But when you disable isolation, for example, it's really hard to be deterministic because if you change your file, that might change how everything works internally.
Cool. Thank you. So there's a second question. When Miri's engine is used to execute const code during compilation, does it run in fast mode with less validation? And how much is the difference between the fast and the slow mode?
Okay, so I'm sort of a rookie in that part of the Miri project. I don't know a lot of Conceivable, but yes, Miri runs without a lot of the validations. It runs when you're running it standalone. So in constant evaluation, I think is faster than what I show you, but just because it has to do less checks. But let's say the engine is the same. It's the same engine, but in a different car. Let's say.
Yeah. So we don't have dynamic allocations in const eval currently, right? So we don't have to check for any of these kind of bugs.
Yeah, but for example, there is this flag in Nightly Rust that lets you run it. I don't remember the name. Is something like Miri Unleashed something. You can run like let's say undisrupted, constant evaluation, all powerful to run basically whatever it wants. And most of the time it breaks the compiler, but yeah, you can actually run like whatever you want using Miri inside the compiler. But that's like super experimental.
Okay. So long term, one could have a VM, like a full functioning VM in Miri.
In principle, yes, but there are a lot of questions about, like, for example, you read a file and then you use that file to, I don't know, create some constant or to define a type using const generic. So that might make your compilation unsound because every time you read the file might change and then you compile it. Or maybe you are using random number generators and you shouldn't allow those inside your compiler. But
So maybe I can introduce my own question here. You think in the very distant future it will be possible to have Miri included in a binary to have Rust as a scripting language inside your Rust program?
oh wow, I have no idea. Actually, I remember that someone was writing an interpreter for MIR directly, so you can use it like it was a REPL. But I don't know what happened with that project.
Was this
Yeah.
the Python like thing? Like
Yeah,
the
but it
Jupyter
worked not.
notebook like?
No, it was a little bit different because it didn't run Rust. It ran Miri, so you have to write the MIR of your program instead of the regular Rust code. But yeah, I don't know
Okay.
what happened with that. Yeah.
Interesting. Another question from the audience. Would it be possible to do this kind of analysis on general LLVM IR?
I'm tempted to say yes. Yes, you could. The thing is that you don't have a lot of the type information that you have when you're interpreting the MIR. So, for example, in the MIR, you have the lifetimes for every single value. You can do a lot of reasoning around that. I don't know if you can do that in LLVMIR directly, but in principle, yeah, you can build, for example, an stack Boros model for LLVMIR if you want, let's say. I don't know how easy it is, but yeah, in principle, you can.
I guess we would have to add a lot of metadata because like new types, for instance, just erase and enums may become just int.
Yeah, I think it's harder, but I believe it's possible to do that.
Cool. Is there anything you would like to show off, like a final use case, or like you have like an idea of like, hey, if someone is bored, maybe give a shot at this project or problem.
Yeah, actually, let me open a new Firefox window here.
I will share. Oh, no. Yes.
So, if you're bored and you want to do something inside Miri, you have a lot of issues here. In particular, we have this. Let me zoom it a little bit because you might be not seeing anything. But we have this chimps label. So there are a lot of really tiny, let's say, really contained problems that you can solve here. For example, Miri doesn't support custom allocators, and in the last Rust version, now box, the heap pointer allows for a custom allocator. So it's super important now to have a way to use a custom allocator in Miri just to be able to test box with different allocators, for example. So yeah, if you're bored, you can just grab any of these issues. Yep.
Very cool. Oh, I'm really looking forward to a stable box with custom allocator support.
Yeah, me too.
That will
That's super
be
cool.
very interesting. Wonderful. So I think we have almost reached the end. I don't see any more questions anymore. It was very well received and great talk. Thank you again. Ferris, thank you as well.
Okay, thank you so much.